In this video, we are going to talk about dot product. Dot product is a way to combine two vectors together to produce a number. So it's kind of like multiplying vectors, but not really, because usually if you multiply two things, you get one of those things back. Here, we're taking two vectors and we're getting a number back, not a vector back. So it's a little bit different. So we're going to look at how dot product works and some of the properties it has. All right, so let's go take a look. So here's a description of dot product. So the dot product of two vectors, and here they're giving us three-dimensional vectors with components u1, u2, u3, and the other one has components v1, v2, v3. If you take the dot product of them together, and we just put a little dot here, which looks like the symbol we use for multiplication, so we have to be a little careful here. What we end up doing is we just multiply the corresponding components together and add them up. Very simple. So let's just do a quick example. All right, so I want to take the dot product of these two vectors here. All right, so notice I just multiply the first two components together, so 3 times 0. And then I add to that the second two components, so -1 times 2. And then I add to that the last two components, 8 times 4. All right, so we simplify this, so I get 0 minus 2 plus 32, so the end result is 30. The dot product of these two vectors is 30. And this works for two-dimensional vectors as well. It works for vectors in any dimension. For 2 dimensions, we would just cut this formula off right here. For 4-dimensional vectors, you would have a fourth pair of components, right? So very simple formula. That's how dot product is defined. What about some properties of dot product? Okay, so properties of dot product. So it says here, let u, v, and w be vectors. And those are going to be written in bold. And then it says, let c be a scalar. Now, I haven't used the word scalar yet, but this is terminology that we'll be using from now on. Scalar is just another word for number. The reason we like to use the word scalar, however, is because when you multiply a vector by a number, if the number is greater than 1, it has the result of making that vector longer. It just scales the length of the vector. If this number is positive and less than 1, it just makes the vector shorter. Right? So it's pointing in the same direction, it's just scaling the length. And so for that reason, we often call numbers scalars, especially when we're going to be multiplying them by vectors. So you'll often hear that terminology. And let's look at the first property here. The first property is the commutativity property. And it says that if you take the dot product of two vectors, it's the same no matter what order you do it in. U dot v is the same as v dot u. Well, that's a nice property, just like addition and multiplication. Then we have the distributive property over here. Dot product distributes across addition, just like this. And it's not hard to show that dot product distributes across subtraction as well. So it behaves just like multiplication of numbers here, right? The associative property, the third one, says that if I take a scalar and multiply it by a dot product, I can put that scalar alternatively on either one of those two vectors and scale them first before I take the dot product. So I could scale u and then take the dot product, or I could scale v and then take the dot product. Any way I do it, I get the same answer. Part 4 here, the property of magnitude. If I take the dot product of a vector with itself, so the v dot v, what do I get? I get the magnitude of v squared. Well, why is that? Can we prove that? Let's just take a quick look. Remember how we defined magnitude of a vector, right? Well, if the vector had components v1, v2, v3, the magnitude of the vector was defined to be the square root of the sum of the squares of the components. Well, if I square both sides here, I get this. And if you look at this, this is exactly the same as just V dotted with V. And so it's a very quick proof to see why that's true. And these properties work in not only in 3 dimensions, but in 2 dimensions, 4 dimensions, any number of dimensions that we define our vectors in, these properties hold true. Next up is a very, very important property of dot product that relates the dot product to the angle between 2 vectors. So if we take 2 vectors, u and v, so let me just draw a vector here, draw another vector here. All right, let's call this one u, let's call this one v. Well, if I put them so that their tails are at the same, emanating from the same point, we can see there's an angle here between these 2 vectors. When we measure angles between vectors, we'll always measure that angle so that it's the angle that's less than 180 degrees, less than pi radians. All right, so I wouldn't be talking about this angle, right, on the outside here. I'm talking about the smaller of those 2 angles. All right, so just keep that in mind. So what is the relationship between dot product and that angle? Well, here it is. Right? If I take the dot product of u and v, it's the same as the product of their magnitudes times the cosine of the angle. Now, geometrically speaking, this is actually a pretty simple idea. What is, let's see, if I take, let's look at this part. If I take the magnitude of u times the cosine of theta, what is that? Well, the magnitude of u is the length of this line here. If I multiply that by the cosine of theta, what am I getting? Well, if you remember from trig, if I were to drop a perpendicular down here, so it makes a right angle with v, if I take this length and multiply it by the cosine of theta, what I'm getting is this length right here, the distance from here to here. So that's the magnitude of u times the cosine of theta. That's a number that corresponds to this length. So it's the extent to which u points in the direction of v. That's what magnitude of u times the cosine of theta is. So really all we're doing is we're multiplying the extent to which one vector points in the direction of the other vector times the length of the other vector. So it's almost like multiplying their lengths together, right? But you're not just taking their lengths, you're taking how much of one vector's length is in the direction of the other vector, and then multiplying them together. And we could do it either way. I could also have looked at the magnitude of v times cosine theta, in which case I would have been projecting v down this way. And I would have been finding this distance. This is the magnitude of v times cosine theta, and I'm multiplying it by the magnitude of u. And it turns out that gives me u dot v. So that, but you could it doesn't matter which vector you project onto the other one, you get the same result. Okay, it always ends up just being the dot product. So this is a really useful geometric way to think of the dot product. Now, how would we prove this? I mean, I gave a geometric explanation as to what's happening, but why is this true? Well, to prove this, what you can do is you can just draw this picture again. All right, here's my vector u, here's my vector v. Now I'm going to draw one more vector. All right, I'm going to draw a vector that goes from the tip of u to the tip of v. Now a question for you is, what is that vector? In terms of u and v, can you write down what this vector is? Pause the video, see if you can come up with that. Find this vector right here. Okay? Hopefully you paused the video and you figured it out. Yeah, this vector here, this vector is just v minus u. if you don't see that, go look back on a couple videos before this one when we talked about adding and subtracting vectors, and you should be able to see from those descriptions why this would be true. Okay, so turns out this is the key to proving this statement. What we're going to do is we're going to look at the law of cosines here. So here's the angle between these vectors. Now, what does the law of cosines say? Well, the law of cosines says that if you have a triangle, let me redraw this triangle just using letters for the, wow, that's a really lousy triangle. A, B, C. Okay, these are the side lengths, right? The law of cosines says that C squared is equal to the following thing. Okay. Oop. Almost forgot the number 2 there. Okay, this is the law of cosines. Well, what is this in terms of what we have written up here? Well, what we have here, C is the length of this side. That's the length of this. That's the magnitude of this vector. I'm taking C squared, so I'm going to take the magnitude of that squared. Right? And then I've got the sum of the squares of the other two sides. So I got the magnitude of u squared plus the magnitude of v squared. And then I'm going to subtract twice the magnitude of u times the magnitude of v times the cosine of theta. Running out of space. Okay, just squeezing it in there. Okay, so that is a formula for this magnitude squared. But we have another formula for this. So I'm going to write this down another way, and then we're going to compare these. Because there's another way to write down this. Just think back earlier in this video. Can you remember something else we said that related to this? Yeah, if you take a vector and take the dot product with itself, you get the magnitude squared. Remember, that was one of the properties of dot product. So in other words, this is just the vector v minus u dotted with itself. Now let's use properties of dot product to expand this out. And it turns out when you do those properties, it works just like when you multiply two binomials together, right? We're going to have v dot v, which is going to be the magnitude of v squared, minus v dot u, minus u dot v, minus minus, that's a plus, u dot u. But remember, u dot u is just the magnitude of u squared, using that property again. Now, what did we say about a dot product? We said it was commutative, so these are the same. Let me rearrange terms. I'm going to put the u first, so moving that guy over here. Then I'm going to write the v. And then these are the same, so I can just subtract twice one of them to get the same thing. So I get this. So we have expressed this guy two different ways, which means that this stuff is the same as this stuff. So this line equals this line. But if these two things are equal, we can subtract from both sides of the equality. I can subtract magnitude of u squared from both sides. I can subtract magnitude of v squared from both sides. So what I'm seeing then is that these are equal. This quantity and this quantity are equal. I can divide both sides by -2. So that means these must be equal. And there it is. There's our formula. We have proved this theorem. And that's why that's true. It follows from the law of cosines. Okay, so what are some of the things we can do with this formula? Well, it's relating the dot product to the angle between the vectors. So we can actually use this to find the angle between two vectors. All right, so let's take a look at an example of this. Suppose I have the vector 1, 1 and the vector 2, negative 1. Okay, I want to find the angle in between. And remember, we're always looking for the angle that's less than 180 degrees. All right, so let's find the angle between these. Okay, well, we know from our formula that the dot product of these is related to the cosine of the angle. So let's compute the dot product. Okay, let's take the vector 1, 1 and dot it with the vector 2, negative 1. Okay, so we take the dot product. I get 1 times 2 is 2 plus 1 times negative 1. The dot product is 1. Okay, what else is in the formula? Well, what else is in... Oh, get out of here, paper. What else is in the formula? We need the magnitudes. We need the magnitudes of those vectors. Okay, let's find those. What's the magnitude of the vector 1, 1? Well, that's the square root of the sum of the squares of its components. That's the square root of 2. What's the magnitude of this guy? Well, it's 2 squared plus negative 1 squared, square root. That is square root of 5. Okay. So from our formula, we know that, let's go look at the formula again. We know that cosine of the angle is just the dot product divided by the product of the magnitudes, right? So cosine of the angle is the dot product, which was 1, divided by the product of the magnitudes. It's 1 over the square root of 10. Or if you want to rationalize the denominator, root 10 over 10. Okay. Now it's easy to find theta. I just use the inverse cosine, or arc cosine. It's the arc cosine of, I'll just leave it like this, 1 over root 10. All right. By the way, if you wanted to get that as a decimal, I actually did compute this ahead of time. Let's just see. That's about 1.2490 radians. That's the angle between those two vectors. Okay, let's just do one more. Okay, I'm going to find a couple other. I'm going to write down a couple other vectors here. This will be a quick one. Notice we don't need to be doing things in a particular dimension. This works in any dimension, 2 dimensions or 3. All right. So what did we do? Find the angle between these. Find the angle between these. Well, first thing we did is we found the dot product. Okay, let's find the dot product. 2 times negative 2 plus 5 times negative 4 plus 6 times 4. Okay, add these together, I get 0. Well, wait a minute. Let's look at this. If I look here, the left-hand side is 0. The magnitudes are not 0, so that means that cosine theta has to equal 0. So whatever that angle is, whatever the angle is between here, cosine of that angle is 0. Well, what angle between 0 and 180 degrees has cosine equal to 0? 90 degrees. So theta is equal to 90 degrees. However, remember, we don't write in degrees. We always go to radians by default. So that's pi over 2 radians. But I will write that just to be extra clear. It's the same as 90 degrees. So very quick, that one. Once we saw the dot product was 0, we pretty much knew what we had to do. Okay. Now this is a very important observation that we've just seen. Whenever the dot product of two vectors is 0, this is going to happen. which means the angle between those two vectors is going to be 90 degrees. And vice versa. If ever the angle between two vectors is 90 degrees, or pi over 2 radians, cosine of theta will be 0, and so that means their dot product will have to be 0. Right? So this is a really interesting relationship, because if the angle between the two vectors is 90 degrees, that means the vectors are orthogonal, or perpendicular. And that's a very important property. And we have a little theorem about that right here. Orthogonal vectors. Two non-zero vectors are orthogonal if and only if their dot product is 0. So if you ever are working with vectors and you find out that their dot product is 0, you know they're perpendicular. That's the really quick way to find that out. Very, very useful fact. Okay. The last thing we're going to do is we're going to talk about projections. This is a very useful application of dot product. It is very often the case that we want to project one vector onto another one. All right, so let's look at an example of this. Let me draw a vector here. Let's let this be, I'm going to call this vector v, and I'm going to take another vector over here. I'm going to call this vector w. Okay. Now what I'm interested in is I want to know the extent to which I want to find the vector that describes how much v is pointing in the direction of w. Okay, so in other words, what I'm going to do is I'm going to drop a perpendicular, and I want to find this vector right here. How much of v is pointing in the direction of w? That's what I'm after. That vector is called the projection, so P-R-O-J. What am I projecting? I'm projecting the vector v. That's the one I'm changing. And I'm projecting it in what direction? Onto w. So I put a little subscript w down here. So proj subscript wv is the projection of v onto w, and I'm getting this vector right here, this guy. Okay, so the question is, how do we find that projection? Well, here's the idea. If I can find the length of this projection, if I can find the length of this vector, well, then I think I can do it, because what I can do is I can take a vector that's pointing in the direction of w but has length 1, so I'll find the unit vector in the direction of w, and then all I have to do is scale it by whatever this length is, and that unit vector will become this vector. So that's the strategy. And remember, we talked about unit vectors in a previous video, so go back and look up that if you forgot that. Okay, so let's just write that down. Unit vector in the direction of w. Well, very easy to do. Let's just call that the vector u, all right? And the way we compute that is we just take w and divide by its length. Very simple. So that's going to be like some vector over here, right? That's going to be u. And I just want to scale u by whatever this length is. So now I have to find the length of this projection. Well, let's use trig again. If I can get this angle, I can just take the length of v, multiply it by the cosine of the angle, and that'll give me this length, right? So the length of the projection, I know how to get that. That's going to be the length of v multiplied by the cosine of theta. Okay. And now all I said I had to do is multiply these two things together. I just need to multiply these, right? Just take this unit vector and scale it by this amount, and I will get this. So that's the answer. But what we're going to do is we're going to write this down, and we're going to come up with a really nice formula, but we're going to have to manipulate things a little bit. So the projection, what we're saying is that the projection of v onto w is this scalar. This is a scalar. It's a number. multiplied by, that's not a dot product, that's actually just multiplication, because this is a number, and I'm multiplying it by this vector, which is this thing, okay? But now let's look at this, v cosine theta. Well, look at the geometry here. U is pointing this way, the unit vector. Theta is the angle between u and v, right? And the length of u is 1. So if I could imagine there was a number 1 here, might as well, that's the length of u. So I really have the length of u, the magnitude of u times the magnitude of v times the cosine of theta, right? Well, that's the same from our dot product formula as just u dot v. So really, I have this. But what is u? U is the same as w over the magnitude of w. Okay, so let's substitute that in. This is a dot product here. This is multiplication. Keep those straight, right? Here I'm taking a vector, dotting with a vector, and I'm getting a number, and I'm multiplying that number times another vector. So this is dot product, this is multiplication. Make sure you can see why that is. And now let's put this all together here. So I've got w dot v. I'm actually going to reverse that the other way. It's commutative, so I can do this. I'm going to write it as v dot w divided by magnitude of w times the magnitude of w. That's the magnitude of w squared, which we said was the same as, well, let me write that down, and we'll change that later. Magnitude of w squared. And then we're multiplying by the vector w. So this is multiplication. This is a scalar, because I've taken a dot product, got a scalar divided by a scalar. That's a scalar. I'm multiplying it by a vector. It doesn't make sense for this to be dot product, because this is a scalar. And another way to write that down, that's one formula for the projection. Another way to write it down is to write w dot w in the bottom, because w dot w is the same as the magnitude of w squared. And this is multiplication, right? So dot product, scalar multiplication. These are two different formulas. I usually just remember this one, because I just like to think of dot product. I don't want to have to remember something else. For the projection of one vector onto another one. So that is a very important formula. Okay, so let's do an example. Let's just do a quick example. I'm going to use two-dimensional vectors just to keep things quick and simple, but it works with three-dimensional as well. All right. So here's our formula we're going to use. Let's use those vectors we had before. Let's say v is the vector 1, 1, and w is the vector 2, negative 1. Okay, and let's compute the projection of v onto w. Okay, well, let's use my favorite version of the formula, this one. I'm going to take v dot w, so let's take their dot products, and we actually did this earlier in the video. We got 1, all right, so v dot w is 1. W dot w, well, we found the length of w earlier in this video too. We found it was the square root of 5. So this is the length squared, like I wrote here, so it's just 5. And then I multiply by the vector w. Well, that's the vector 2, negative 1. Let's go ahead and distribute this scalar inside. So it's the vector 2/5, negative 1/5. Nope, off the screen. There we go. Now let's do it the other way around. Let's project the vector w onto v. Let's do it that way. Well, here I'm going to take w dot v divided by v dot v times v. So the v's and the w's are changing roles here. All right, w dot v is the same as v dot w, so I'm still going to get a 1. But now I'm dividing by the length of v squared, right, which is 2. And I'm going to multiply that by the vector v, which is the vector 1, 1, which when I multiply that out, I get 1 half, 1 half. Okay, I just wanted to show you a pictorial representation of what we just did here. Okay, here we go. So here we have the vector 1, 1. The first thing we did is we projected that onto this other vector, 2, negative 1. And so when we do that, we got this resulting vector. And you can see all we did is we dropped it down orthogonally, and then we ended up with this vector. This was the answer to the first problem we did, right? The vector 2/5, negative 1/5. Okay. The second thing we did is we projected the vectors the other way around. We projected that red vector here, 2, negative 1, onto the vector 1, 1. And when we did that, we dropped down orthogonal, and then we ended up with that vector. That's the vector 1 half, 1 half. So these are the projections. So this is just a picture of what's going on here. And that is it for this video. Properties of dot product, and in particular using it, relations to angles, and then using it to make projections.